Hello again. Yeah, it's kind of awkward saying that hello again, but hello again. Today I'm going to be modeling a higher order mode coupler. This is not going to really be about describing what a higher mode coupler is, but I think maybe just a brief overview. So, higher order mode couplers are used to extract parasitic modes which are excited by beams in accelerating cavities. So, they come in different shapes and sizes. Been playing around with a couple of models of late. So I want to start a new design and thought to record it, or not a new design, but an old design, but modifying it to suit my purpose. So just pulling up, and this is going to be in real time, maybe speed up some parts, but just to show couplers, they come in different shapes and sizes, and found this paper. So yeah, these are basically couplers and they're attached to cavities. Of course, you've seen a cavity here again. And yeah, something like this is 3D. Let me see, I think there should be a better image. Yes. So structures like devices like this, and like I mentioned, used to extract high order modes from some parasitic high order modes from cavities, accelerating cavities. We are not going to be modeling this today. I've already modeled that, but today I want to model. Actually, had a call. So let's see. Where did I stop? Coupler we are modeling. I am modeling today. Something like this. I think I should have a better. I think I should have a better picture of this. I can't find a better picture of this, so not to waste time. Maybe when it's done, you'd see it. So for now, I think this picture suffices. So I'll be using this as a reference and modeling it now. Um, this was designed for the Tesla cavity. So the dimensions you see are actually for I think 1,300 megahertz. So I'm going to be manufacturing some dimensions based on the couplers I've designed before. So I'm not going to be using exactly these dimensions here, but the I'm going to be using that as my reference image for modeling the coupler. So, okay, maybe I should just show a bit of the couplers I've been modeling. So, if I could show this. So, this is just a concept design I was working on. Then, this is another design. So, this is just one notch, and this is a double notch. Is that? And this is a double notch, and yeah, just playing around with different geometries and checking out their properties. Hook top and hook bottom. And this is actually the LHC type hook coupler. And so, yes, back to the business of today, modeling. So as usual, we'll go to high frequency, and of course we're not interested in the analysis now. We just want to get a model, and always first things first, change your dimensions to whatever you prefer. I prefer working in millimeters and megahertz. And maybe I move this a little bit up here. Okay. So since we always want to work with parameterizing the shape because it's easier then to modify and tune and optimize and all of those things. So I'll just be typing in some dimensions. Maybe I make up some as I go, some I didn't foresee, and maybe I just download this image so I could always just pull it up and save quick presentation. Yes. So save the image, or so small. So save the image so I could always just pull it up anytime I want to. And I close the whole of my windows. Okay. So the image is actually open on our screen, and I would go from there. So first thing I always start with is my beam pipe. My beam pipe, my beam pipe radius, which is 150 for the cavity I designed, which operates at 400, the fundamental frequency of 400 megahertz. So it's 150 millimeters in the beam pipe is 150 millimeters in radius. So what else would I need? I think, okay. So I'm going to be, how do I annotate this stuff? Edit image. Maybe this. I really can't see. Maybe paint. Enhance your photo. No. Okay, this doesn't work. So I'll just use my mouse to show it. Hopefully. So I'm going to be calling this length from here to here. I'm going to be calling it L1. Then I call for some specific reasons, but I won't go into that. Then I'll call this the LM. Then I'll call from here to here. That should be the second length, L2. Then yeah, I think I'll just keep making the dimensions as I go. I think that'll be best instead of trying to get everything at once. And I know this because from experience, I mean I've modeled a couple of couplers, so I could guess the dimensions that I actually need to fully model the coupler. So for now, I just have the beam pipe and of course a cylinder, and then you press the escape, and yeah, we have our definition. So for the outer radius, I have my Ri. Now for the actual diameter of the casing of the coupler, okay, yeah, I didn't specify that. So that's the first dimension I'm going to make up, and I'm going to call that the D tube. Um, okay, the length of the coupler. That's what I have to put in first. So I want it to be centered. So I could call it D tube because I want my tube to be right 2, then plus offset. Now don't bother too much about the dimensions. You could as well put anything. So I could preview this, and then D tube is not defined, so it pops up this box for me to enter D tube and 103. And these values are from the previous couplers I modeled. And description, diameter of antenna tube, yes. And then offset, of course, offset is just okay. I'll explain the offset later. So but then I always use 20. So yep, preview, and then I could look at it this way or this way, so 3. But then something is wrong because it should be minus, and then this also should be minus, so it is centered. So preview, something is wrong. D tube divided by 2 plus offset, and D max is this preview. Now what is wrong with this? Aha, there was already a minus. Yes, so well centered, offset correctly from both sides, and then I can click OK. Oh, I forgot something. I have to change the material. So assign material. So I'm using, it's going to be vacuum. So we have our beam pipe. Now let's go over to building the casing for the coupler, for the antenna. So I go to cylinder again and escape, and then I want the cylinder to be aligned in the Y direction. So I click on the Y. Then I have the outer radius, which is D tube divided by 2. And then the y max, what height should I give it? I would call it okay. Now here's where some calculation actually comes in, because I want this height to be I want this height to be this length plus this length plus this length, then maybe plus a little space on top that I'm going to call something else. And yeah, there we have it. I think I should have a better image of this. Come in, let me pause. And I really couldn't find a better image, so I guess I'll have to work with this. So like I said, I need to make the total height. Okay, I also have to factor in some penetration depth. So I would want, or maybe I could just model it and then fix whatsoever errors that could arise later. But then, yeah, general idea is I want this height to be the maximum point to be, because this is our zero, and then I want the maximum point to be this length plus this length plus this length, then plus a little gap which I should call maybe T T. Yes, TT or GT. Yeah, GT gap. So a gap, and then that's that. So yeah, let's see if there are any errors. I would correct them as we go. So let go. So I need the maximum to be L1 plus L2. Now, bear in mind, I haven't defined all of this yet, but then it's going to bring up a pop-up for me to define it. Plus LM plus L2, then plus GT. Yes, I call that the GT. And then I need a penetration depth. Okay, I don't think I actually need. Okay, even if I need it later, then I'll just come back and fix it, because with CSC you could always go back in the history tree and make some modifications and run it again. So this is going to be vacuum and adding to component one, and let's preview and see. So L1 not defined, of course it's not. I would call this maybe 100, just giving some random values. 100 LM maybe 15, and then L2 maybe 140, and GT maybe just 3 millimeters. So okay, this is actually short, but then I could always modify the values here. But then something is missing, because I actually need this length to be plus. Okay, it's not very short, because I didn't consider the radius. So yes, this looks okay, a bit long, but okay, we'll work with this. And okay, that's that. Insert none to all, so it doesn't perform any boolean operations on any of them. So we have this. We're making progress. So I'm going to turn to this orientation, because we have it facing this one. Then the orientation actually matters in the design of these couplers. So now we go for the antenna. Let's see. I wouldn't perform any boolean operations. You see, the solids are separate. So I'm going to leave it like that. And we start with the antenna. So, okay, first of all, I need some dimensions from this, because I usually model from top. I model from top to bottom. So I need the highest point, and then I just keep subtracting. So new cylinder, escape, and then oriented in the y direction, and then I need the outer radius. Now d I'm just going to call it d1, and then the y max is going to be the same as the x, but then remember that we have an offset here, so I'm going to remove that from the that is GT. We have a gap. So I'm going to remove that, and then this is going to start from below. Okay, of course, I'm D1. I could use 16 millimeters. Okay, you can't see it, but then it's actually there. It's actually there. But then I have to complete the operation before we can see it. So, but then this is going to be a perfect electric conductor, which is PEC. And then, okay, so now I can view it. And this is it, but then there's a problem because it's not supposed to extend all the way down. I try to model it bit by bit. So I have that this is going to be removing the L2. And yeah, that's we have it there. So what we have currently is just this top piece with the gap. So we've modeled this part of the antenna and we just keep modeling like that. The next would be this piece, and then the next would be the final piece. Then we go add the other bits of it. So that's for the first. And the second part of it, which is the LM part, of course, it is another cylinder, although a very short one. So we go and just to mention, it's not always compulsory that it's a cylinder. You could actually have a square geometry with fillets, and that is one of the things I'm trying to look at in geometry, how the shape, the cross section of the antenna affects the properties. If it's better, maybe machine wise machinability, if it's better, and maybe also some other mechanical properties, and maybe also thermal properties. So that's what I'm currently looking at. So again, we go in the Y direction, and then the Y max now continues from where the last one stopped. And then, so you see what I'm doing, I just have like the total length, and then what I just did is subtract improper radius. Please check. Okay, the radius is going to be the same as D1. Okay, it's supposed to be D1 divided by 2 because I'm working in diameters. Why? Strange reason, but won't say today. So yes, this, and then I have to change this one also to D1 divided by 2. Yes. So we have solid 3 and solid 4. Then we continue to model the remaining part, which is oriented in the Y. So it's just like repeat. Then this time we take this out, and then this time we take this out. So the outer radius is the same, D1 divided by 2. And voila, we have some parts of antenna. So just have it in 3 parts, and it's actually here. But then I'm going to, I mentioned the penetration depth initially. I'm going to try to include that, but then for now, I'll just, because then I just have to define a variable. Okay, I'll just define it now and call it PD. And I'll put this at 25. And PD actually determines how far this antenna is dipped into the beam pipe, how far it goes into the beam pipe. Now, what next? Let's model this, then we go over to this. So, of course, it's another cylindrical section, but this time it is oriented along the X. So what's the radius? I use D1 divided by 2 again. And then what's the X max? We see that the X max is around here or this side, but then I'm following the image. So I put D tube divided by 2 and then 0. But we need the Y center. So the Y center should be at around, this was LM, so it should be at LM, but then LM divided by 2. Yes. So it's positioned correctly, but I think this is 3, this is 2. Yes, so there we have it. I'm using 3, maybe I use 5, yes. So there we have it. Now I just switch from 3 to 5. I mean, it doesn't really matter because you could model it anyways, and then when you couple it to the cavity, you just have to change the direction, but trying to be consistent with the figure. And yes, we have that, and that was very easy. So also perfect electric conductor, and yeah, that's that. Then for the notch part of it, which is this, I'm going to be using sweep operation. So I'm going to be using a sweep, and we're going to start with a sketch. So um, this is what we have. And if you notice, I haven't performed any boolean operation on it. I usually like leaving it that way until I'm done with the entire geometry. So for this part, how do we approach this? I'm going to use curves. So we have a straight section. Okay, I'm just going to explain with the image. We have a straight section, then a bit of a semicircle curve this way, then another semicircle, no, quarter circle curve this one, quarter circle curve this way. Now the important thing is getting the dimensions right, and also parametrics, so that when you update the size, change the size of one parameter, it doesn't mess up. It doesn't give you a degenerate geometry. It still gives you exactly the same thing, but then scaled depending on the dimension you use. So we go to curves, and then line. So we have a line section initially, and I'm just going to click on anywhere. Maybe I start from the center, and then it doesn't really matter because you're going to be defining the dimensions anyway. So this pops up, and I want the x1. So this gives just x comma y, x1 y1, and x2 y2. So this is x1 y1, and then this is x2 y2. So I want this to be from the center. So I preview. I want this to be from the center, but then it's not x not. X naught is supposed to be 0. Come in, let me see the axis. Okay. Now, one thing also about the axis is that this is the global axis, and luckily it corresponds to the plane on which this geometry, this piece of the couple actually lies. If not, we would have had to go to a local geometry. Maybe I'll do that in a separate video, or maybe there's a part of this that actually requires that we translate to a local coordinate system. So this is supposed to be 0, but I click on preview and it's not showing. But then, yeah, let's just continue. So y1 has to be also parametric. So I would have it at L1 currently, and this is going to be the same because it's on the same level. But then it's not going to be at L1. I want it to be just, let's say, um I call it notch height nh, and I'm going to define nh just so I could easily change it later. So I call nh maybe about, let's say, 25 centimeters. So nh would define the distance from the bottom most point of the antenna to where the center of the notch is located. So yeah, and that's that. And then I want x2, the length. I want the length to be, what do I call this length? I call it L notch. Yes, ln. Hope that's correct. Yeah, I'll just call it. So ln, I want it to be, let's say, 25 also. Let's see how long that is. Okay. So that's that for curve 1. Okay, it actually starts from the 0 point. We just weren't in it because of the 3D geometry covering it. So the next would be an arc. or we could use a spline, but then I prefer arcs because I could easily define dimension. So for the arc, we click on the center and then click on the point it crosses, and then we could go either clockwise or anti-clockwise, but I'll just leave it this way. Just double click, it doesn't matter. We actually want it to go this way, so what we do is we click counterclockwise and then we look at it flip. Then the center would now be this, which is ln, that's the x center, and then the y center is what we had initially, which is what's that variable, nh, notch height. So that's this, which is the center, and then I want it to be 90 degrees. I want it to sweep 90 degrees, and then x2, y2. I would have to define a different dimension for this. And okay, what I'll do is I'll try to define the x2, y2, which would be this point here. Okay, which will be this point here. I want to define it as an offset from the tube walls. So I could say maybe I just call it offset of the notch. So ON. I'm just making up these names, these variable names. So I want it to be offset from D tube minus offset of the notch. And that becomes, or rather, I would actually make it a radius, because since we have that this is just a quarter, so from here to this point is a radius, and then also this should be a quarter also, and then from, I want it to be that from this point to this point is also a radius. So what we have is that this is one radius, and then this is a second radius. So I want to make it such that the total length is a diameter, so I'm going to call it the radius of the notch, Rn, instead, and the x to y2 is going to be minus Rn, so d tube minus Rn. And what am I going to call Rn? And now okay, and now Rn, I want Rn, maybe I pull up, okay, maybe I have to actually calculate this. So I want I want the geometry to be such that, okay, now I notice something, that the coupler is actually offset, but that is no problem. We could actually make it offset a bit to the left, so we could make that correction. I just noticed that now. So I actually want such that this always meets the wall at this point, so it's going to be dependent on what, where do I fix it to? Okay, maybe I'm not just going to fix it to anywhere. It would maybe become clearer as I go. So, but then I know that the name of the variable is going to be Rn, and then x1 is supposed to be Ln also. No, x1 is supposed to be Rn. Is it? No. Y1 is going to be Rn, and x1 is going to be d tube minus Rn. So let's preview, and I'll call Rn maybe 30. Okay. It's now going somewhere else. So what is missing? X center is Ln, which is this point, plus Ri Ln. Then, sorry, this is d tube divided by 2. And x1 is equal to d tube minus Rn, where Rn is 30. And then y1 is supposed to be, okay, y1 is not Rn. Y1 should be Ri plus nh plus Rn. Yes. And no, counterclockwise. But then something is still missing. Maybe I'll pause and then figure it out. Okay, actually found the problem, and the problem was that x1 y1 actually defines the initial point. Then you have your angle sweep. If you didn't want your angle, then you would have been able to define x2 comma y2. So this was the problem. So x1 comma y1 is at this point, and then y1 is also at this point. Then we have our center at this point. Then we have Rn. Now from this we could see that Rn is obviously too big, so I'm going to reduce it. Okay, so I'm going to reduce it to 15, and then parametric update, yes. Now for the second quarter circle is going to be again our center point, which is going to be somewhere here on the wall. Then okay, actually this circle instead of an arc. So an arc center point somewhere around here. I mean, it doesn't really matter, but then something like this. Yes. So we have to fix this now. Our center, it's going to be at this point. Then our x1, our center is going to be somewhere here, and then x1 comma y1 is going to be somewhere. No, our center is going to be somewhere here, which is going to be on the wall because we want it to be always exactly at the wall. So of the tube, and then our x1 y1 is going to be this point. So let's define our x1 y1, which is ln plus rn. Then our y1, remember this point is ln plus rn. Then our y1 is going to be ri plus what? So this point is going to be ri plus nh plus rn plus nh plus rn. So let's preview that. Yes, it has moved to this point. Then we have 90 degrees. Preview. Yup. And then we have our center to be at the wall, which is going to be d tube divided by 2. That is the x, which is going to be at this point. Then we want the y to be at ri plus nh plus 2 times rn. Okay, that doesn't work. Something is missing. Where's our center? Center is at this point. Our center is at this point. No, it's not counterclockwise. No, it's clockwise. It's at this point. And what's this point? This point should be d tube divided by 2, which is, yes, which would give somewhere around here. Then the problem should be with the y center, which is ri plus nh, which gives this line, then plus rn gives, oh sorry, not 2rn, plus rn. Yes, yup, got it. It's kind of tricky sometimes. So we have geometry. Now remember the offset I mentioned, it's not going to be a problem. We just need to go back to each of the shapes, and then this is one of the reasons why I don't like combining the shapes until I'm done with the modeling. So for that shift, we're going to go back and then move the offset the antenna from the axis. It's already a very long video, but yeah, I'll just go on because I want it to be in real time so you could also see the mistakes. And now we have to sweep around this, and then we see that we can't really, okay, we need to wait, I'm coming. So selecting the curve, now we need to build a circle which should be exactly perpendicular to this curve. So one way you could do it, if I am lucky, this would already give me, so I click on P, or I could just go here and then pick points. Where's points? So I could click on S or click on P. I don't know why P is not here, but then P also picks point. So you could also click on X S. Okay, you could also click yes, P. Pick endpoint. So that's it, P. So I could click on P and then double click on it to select it. Now I want to align the axis, which is going to be a local axis. Now, if I'm lucky, because this doesn't really specify in what direction, in what angle to the point, because the point is a free point. But then I'm going to align it, and hopefully it gives me something I need. If not, I would have to look for some other way to actually define the coordinate system first, the working coordinate system, and then now before I draw my circle. So, yep, we are not very, or I am not very lucky because it doesn't align it. It gives a still the same axis, but then different. Now, I could go to the local coordinate system properties and then I could actually make a different normal now. Now, this is where some modifications have to come in. So I go to 5. And now we see that currently still aligned your UV, which is your local coordinate system, is still aligned pretty much with the global coordinate system, which is XY. The only thing that happens is that it was shifted from this point, so I could click local coordinate system. So we see the zeros of the global coordinate system on this plane being here. Now, if I should click on this point P and align, it's still pretty much aligned with the XY. So we could change that by going to the local coordinate system and then modifying the properties. So currently the normal is in the Z. So what I want to do is I want to change the normal to the X. So this becomes 0 and then I put this at 1, then I preview. The normal vector and the U vector are parallel. So I'm going to change the U vector to the Z. And voila, what I have is now an axis which is perpendicular. Okay, let me get this. Yes, which is exactly perpendicular to the plane I want my circle to start on. So that's it. Define the normal x, but then the normal was the same in the same direction with the u vector, which is not supposed to be. So I had to change it to z. I mean, I could also, let me try. I think I could also change it to y. It just changed the orientation, but then that doesn't. So we see this. It just changed the orientation of the u. So that's not really important. We have our plane, and then I click on OK. So now I can now pretty much work on this plane. So my UW, and this is now the positive view. Going this way is positive view, but then that is not very important. What I want to do now is to draw a circle, and yes, I could radius. Should I give it? I think I could give it the same radius as the overall antenna, and then that's d1 divided by 2. Hopefully that's correct, but then again we could always go back and change it. So I've gotten my circle and I'm quitting from the local coordinate system, and voila, I have my circle there ready to be swept off their feet. Okay, not actually off their feet, along this part. So for that, I could do one of many things. I could either go to click on circle, then click on sweep curve. Now when I click on circle and click on sweep curve, it is already selected. It is already selected as the profile to sweep, to be swept. So I just have to press enter, but then escape. I'm going to make a demonstration. If I didn't click on the circle and I went directly to sweep curve, then it selects everything. It selects everything because I selected the curve. But then if I selected just a solid and I went to sweep, then it tells me to double click to select the profile to be swept. So I could either select it from here or double click on the circle. Wait, yes, double click on it and then it highlights here, so I know it is selected. Then I press enter, and then it's not telling me to select the path, and then I select, double click on the path, and voila, I have my sweep. And now I could go to delete the parts. I don't really like deleting the parts. I'll just hide it later. Then you could select some other things like your twist angle. Then the material, of course, is still PEC. And okay, there we have it. And you could see the solids that we have already forming and already almost looking like this. But then to maybe I'll end it here. Okay, I won't end it here. I would actually. Oh, we are not done. We need an extra bit of an extra piece here, which I'm going to model because the video is already getting very long, almost an hour. So I'll see if I can speed this up. But first of all, I want to give this an offset from the zero of the y-axis. So I want to give it an offset, and I could just define that as what do I define that as? I could actually use L, which is the length between this point and this to offset it. But then how do I do that? Hmm. Okay, just because I do not want to spend so much, or I could actually pause and then come back, make the calculation, then come back to see how I could drive it. Now, the goal of this is to give at least define your geometry with minimum dimensions as little of dimensions as possible, because then when we want to tune this we have less parameters to work with. So it's defining it completely but then using the minimum amount of dimensions to use it. So it's why I'm trying to, because I could just create another offset and then we have that, but I'm trying to drive it with some other dimension. So we could just define this length from this point and then it automatically shifts it. So I'll be right back. Okay, so made a lot of changes to the geometry just to, I mean, it's kind of important, but I won't really show it here. But then basically, just in a bit to make this parametric, I modified some things, and then one thing I also observed was that in defining the circle, the local coordinates, I the parameters here were actually not updated, so I had to update it and move the circle again. Just made a little adjustment so that the length, like I mentioned, so I use this length to actually control the position of the entire antenna. I use to control the position of the entire antenna. So I mean, when you want to make your model, you make calculations beforehand, but I was just doing this ad hoc without any dimension. I mean, I really don't. This is my first time modeling this, so I don't really have dimensions for the Tesla, the Tesla higher order mode coupler. So it's just winging it. So I hope that when you model yours, you actually have the dimensions and then take time to draw it out and all. So now that I've actually gotten an idea of how this works, so basically I'm taking my reference from here and offsetting every other thing with respect to this. So this is the radius I define here, which is Rn. So this makes this point, the x coordinate of this point, 2r. And so every other thing is just going to be from here. So currently my length is 25, so I could shift my length to, let's say, 35. And then what? Intersecting paths. Sweep operation field, intersecting paths. Oh, come on. I have to wait, something is not right here. If I should change it to 25. Yes, I think I know the problem. Yes, process entire is released. Yes. So I think I know the problem. There are still some variables that are dependent on there are still some variables that are dependent on the initial ln I defined. So I'm going to pause now and then tidy everything up. or I could, no, I'm going to tidy everything up because it's kind of difficult talking and then trying to analyze the problem and also analyzing the problem itself. So I'm just going to pause and then come back. Okay, so that is fixed. I really wish I could talk and I really wish I could talk and then explain it. But then basically, what I did was I went back to my history tree and kind of deleted. I think the problem was with the defining the local coordinate system because for some reasons that really cannot be parametric even when you type in the parametric dimensions when you come back to it. And what I mean is, if I should go to, let's say, local coordinate system and then I check out the properties, you see it's x is a fixed value. So even if I were to type in the parametric, because I could get the parametric value for this and then type it with all the variables, when I come back to it, it changes to it changes back to just a fixed value. So while you can walk top to bottom, you can't really walk bottom to top. So and then when you go to your so you just have to be careful. But then when your history list is processing it, it processes from top to bottom. And that's not really a problem because it does one thing after the other. But then the problem was I was working from, and that's if you notice now I've consumed the sketches, so they are no longer available for me to fiddle around with. Because if I should make any changes now, it appears down in the history list. So if I should make any changes that should have been reflected in the past, it doesn't get reflected in the past, but then in the future, if that makes sense. And then this doesn't work. It generates degenerate geometry. So um I think for that, if you are not maybe very comfortable, or maybe for now, just the early stages, just consume the sketch instead. So proceeding, so I fixed it, and then you could see that changing this only update your parameter, changes to 50, it only affects the length. So now let's move the other parts of the geometry along with so that's the antenna. So we're just going to go back in time and then adjust this adjust this to x center. So what we are shifting is x center. So it's been on the 0, but then we want to move it with d tube divided by 2, which gives us from this which gives us this distance. Then we want to move it minus, okay, I actually did this calculation, so it's going to be minus l n plus 2 times r, and you could check this to be correct, and we'll see that in an instant as it moves the top part of the antenna. So I'm just going to be copying this, and this is gives it an okay. Let's see the history list. So for your what do they actually call this? Yeah, there's a name they call it, but I've forgotten. Okay, maybe I'll remember later. But for these your primitive, exactly, primitive shapes, if you should make an adjustment to the dimensions, it doesn't come as a new activity in the history list. It automatically changes the definitions in the past, if that makes any sense. If hopefully that actually makes sense. But then when you make your changes in the curve and then your local coordinates, it doesn't automatically get updated in the past. If you wanted to make a change in it, you would have to come to the history block and then edit it from here, if that makes sense. I think that, yeah, that should make sense. So instead of, and that's why I think, okay, for now, just consume this sketch. Forget about what I said initially, just consume the sketch. Because then if you still have the sketch here, then you'd be tempted to work on this instead of going back in time to change the dimensions that you need. So we just apply the same shift to all of them. So your X center is just shifted by this, and then okay. So see that it's pretty easy to make some adjustments in case you didn't make them initially. You made some mistake in your design. And then for the last one, we move X minimum to this. Yes. Voila. And there we have it, the antenna. Now, there's another part. I think I could show that maybe more clearly in 3D. Where do I have this? I always lose this. I'll just pause. Oh, great. I found it. I found it. So this is what we have, something like this is what we have. Then we have this other piece. I hope it's still recording. Yes. Then we have this other piece connected to it in this manner. Then there's a space here. I could zoom in. And then there's a little space here. So we are going to be modeling this now. And what method could I use? I mean, to model this, I would have to combine all of the all of the shapes, or I could. I think there are many ways to go about it, but I'll just go along with the one that feels right for now. So first of all, I boolean all of my shapes, and so I have just one piece. Then I could now perform an operation. Now, making a boolean doesn't mean I can't go back to edit it again, just that I prefer it to be separate, because I could always go to this point and then I could see my individual shapes, and then double clicking I could always make whatsoever edits I want. So after creating the boolean, I want to create a kind of curve. Now, if that curve, the nature of the curve actually affects the the properties, I have no idea since I haven't modeled this before. But then I think when I'm done, I could study it and check the geometry. And to do that, I would try and make it as parametric as possible. So first of all, since this is a quite complex geometry, I think I'm going to use curves, because it's not very clear. It's not very clear how this kind of connects. Like there's no, okay, there's this which just shows this. So I think I could just cut it. So I create a kind of profile as this, and then I create this sort of shape and then subtract it. So let's jump right into it. I go to curves and line, and I just draw a random line. Remember, we're going to define it later. So should I be worried about the dimensions? Okay, I think I'll just get right on with dimensions. So I want the x to be the midpoint. So x2 is also the same. Then, oh, you can't actually see it because of this, but then I can't. Okay, I'm just going to leave it like this for now with this y dimension. I'm going to come back to change it, but then just to show what it looks like. So this is what we have. Now, I want the mid of this line to be the same with the mid of this other line, which is our LM. So I could go to this and copy some dimensions. So go to define, yes. So the Y position of this is Ri plus L plus LM. So I go back to my line, define line, and then I make it parametric. So this is going to be, since I want it to be at the middle, this is going to be, y1 is going to be at the middle, but then I'm going to create a different, a new dimension. Now this is going to be the middle, lm divided by 2. So lm gives here this point, but then lm divided by 2 gives the middle. So I'm going to be offsetting it from the midpoint. So I'm going to put I'm then just going to put c, which is for chamfer or something like that, and c offset or c length, lc. I'll just call it lc. Now whether this variable actually plays a role in the properties, the transmission properties of the coupler. Later, I would have to investigate that. Then minus LC. So then, of course, they're going to ask me to define LC. I might just call it 25, as if I like 25. So there we have it. And this line is perfectly centered on this. And then from this, the distance between here and here is 25. And then here is also 25. So we got that. Now, just to make my life really, really simple, I'm going to be making this a kind of block shape, of course. Now, like I said, you could actually model this in several ways. And now I just thought about a different way I could do this, which is actually much simpler and it doesn't involve curves. That's cool. So I'm going to delete this curve and this line I just drew, and instead I'm going to be modeling it with a rectangle. So the x main is going to be, of course, as oh come on, I missed that. I'm going to make it. This should be y max, and this is y mean. So I'm going to have to copy the other dimension, or I could just type it. So this is minus. What did we have? LC. Y max should be plus. I mean, it doesn't really matter. And y mean should be minus LC. So then we have our x to be d cube. Hopefully I remember it, divided by 2, then minus ln plus 2 times rn. And then these are x mean. These are x mean, which just falls along here. So I'm going to be offsetting it a bit. No, I think that's it. And x max is going to be something a little bit offset to the side. Hopefully, I don't know how this camera is oriented, but then something offset to the side. Doesn't matter the dimension, since we are going to cut it off anyway. So I'm going to make it yeah, I'm just going to make it d tube. So that's the x max position. Then your z max, let's see, 5. I'm just going to make your z max d1 divided by 2, which is going to be d1 divided by 2. So it's going to be, so preview. Okay, now this is looking totally wrong because it's on the opposite side and I just have to move it this way. Minus d max. Yes. Yeah, that's cool. So minus d tube divided by 2. Yes. So what I actually want is a kind of geometry such that this totally cuts off some point. So the dimensions, the other dimensions of this rectangle is actually not very important. The other dimension is actually, it's not very important. I just need something that would remove part of the shape. So I think this should suffice. And okay, so what I have now is this and this. So all I need to do is to perform a boolean on it, and I am going to subtract from this. So I click the shape I want to subtract from, and I click on a boolean subtract, and then the shape I want subtracted from it, and then I click on it and press enter. So voila, this is what I have. Now, of course, I could have made room, I guess, for the distance between the center, the middle of the antenna, and this point to see if it actually plays a role. The if it plays a role in the transmission properties, but then that would be for maybe some other time. I mean, it's worthy to investigate. So we actually have something that looks like this, but then it's not quite. And then we usually avoid sharp edges when modeling electrical stuff. So to get this, it's just an easy task, which is filleting. So I'm going to click on E to select edges, and I'm going to select these two edges, and I'm going to blend. Okay, it's called blend here, but it's filleting. Then I'm going to select a blend radius. I'm going to call it blend, then preview, but then I haven't defined blend, so I'll just make it 10. Yup. I think it's a big, so I'm going to make it, okay. Yeah, what do you know? That actually works. 5. And voila, we have something looking like this. Yup. Then for the last bit of it, this is actually not very difficult since it's kind of almost the same as this middle piece, but then on the opposite side. So this, and I need this piece, of course. So I'm just going to copy this dimension. No, it's actually the center that I need. I need the center. So cylinder, escape, and then I go to outer radius. I'm going to call it a different thing, which is D2. Divided by 2, and inner radius nothing. I want it oriented in the along the x, and x marks, it's going to be, now I'm going to define a new variable which is going to define the separation between this point and the head. Maybe I show it here. So I'm going to call this separation maybe CT or something like that. So I want the x minimum or maximum, anyone you choose to call it, it doesn't really matter. I want the x minimum to be, no, this is y. This is the y position. This is the y center. So then I want the x minimum to be d tube minus ln plus 2 times rn, then minus, okay, I'll just put plus inside the bracket, ct. Then the x max would be, I mean, I could just as well put any length at all, but I'll call it, let me call it lt. Hopefully I haven't defined lt initially. Nope, I haven't. But then it doesn't really matter. It could be as long as it wants. But since it's connected to the output anyways, so preview D2. I want to call D2 14, and I want to call CT. What CT? Okay, the separation. Let me use 3 millimeters, and LT. Maybe I could use 150. No, that's too long. 100. That's still too long. 50, no, yeah, 50, 50, it's okay. Okay, now this is positive, so I change it to negative. Oh, come on. Okay, that's the problem. This is d tube divided by 2. I really should work with aha. Now it's too short. So that's it. And okay, but then I want to change this to maybe 100, and parametric update, and voila, we have solid. Then I mean, I could copy the head style of this. And how would I do that? How would I do that? I would use a circle, and let me see a cylinder, and let me see if there's an option to taper. Segment 0. So there's no option to taper the cylinder. So I'll just, I think for now, I'll just use a cylindrical head, and I'll just use a cylindrical head, and then I need some dimensions copied. So I need the x minimum instead of having to calculate it again. So I'll show you my alternative, which is going to be, I'm going to call it dt, outer radius divided by 2. It's going to be oriented in the x. Then my x mean is going to be this. And then I'm going to define a new variable, cap thickness. Cap thickness, and okay, back to our reference image. Our reference image actually has it as a cap, something like that, not this other one that looks a bit complicated, although it's not very complicated, but just to save time, which is already fast spent. Yes, then Y center is going to be, oh boy, Ri plus L1 plus Tm divided by 2. I hope I have Tm. Is it Tm or Lm? I think I'll just have to change it later. Lm. So preview dt. What was dt? Okay, the diameter of the cap. I'd call that let's say 12 diameter. So it should be more than, so let's say 15, and then I'll call this dt divided. Okay, cap thickness. I'll use 5 millimeters for cap thickness, and yeah, of course, this is supposed to be plus cap thickness. Preview. Yes, voila. So I may need to increase or reduce the cap thickness or the DT, but I think instead I would reduce CT, no D2, maybe to 10 or something. Yup, voila. And increase DT to maybe 20 or something. I mean, remember, this is just like a random modeling. But then when I look at the transmission parameters, then I could now know how to tweak it and which variables affect which parameters and which points in the transmission curve. Now this is almost done, but then we need some extra bit of geometry for the shell itself. And oh, I mean, you could also blend this, but I think I'm going to leave it this way for now. Then the last bit of geometry is going to be for the shell, which is also going to be a cylinder. But then first of all, I have to copy the geometry and some dimensions. So I think what's most important is, yes, AC. Okay. Escape, and I want it oriented along the X, and outer radius, I'm going to define it as DZ. Yes, and I'm going to tell you why in a second. So X min is going to be this, and X max is going to be this. Then Y center, of course, Ri plus L1 plus Lm divided by 2. Preview. DZ. Now DZ is going to be 2.034. Hopefully this is correct. Multiplied by L. No, not LT. Multiplied by, what did I call this? D2. I think so. Yes. So you may be wondering where the 2.034 value is coming from. The goal usually is to terminate the coupler with a 50 ohm standard transmission line. So the ratio, it's 2.0, either 2.30 something or 2.03 something, 034. So that's what we want to terminate it with a 50 ohm standard transmission line. So that's why I just use the ratio instead. So I want X max to be minus LT. Yes, so I have this, but then yeah, I mean, it wasn't important to start it from here, but then when I combine it with the main shell, it just becomes, this part goes away. So I make it a vacuum, and I think this should be okay. Yes, none to all. So voila, we have our Tesla coupler, but then I could just do some tidying up and then combine the outer shells, and then I click on Boolean, and that's it. Yeah, hopefully. So just to confirm the ratio quickly, it's 42.4 divided by 18.4. So yes, 2.304. It's 304, not 034, 304. So remember, this is to terminating to a 50 ohm standard transmission line, 50 ohm standard transmission line. So that's the ratio 2.304. I haven't saved it. I haven't saved it. Where should I save it under? I think I save it under couplers. And I'm going to call this the Tesla type coupler. Now, of course, I'm going to maybe try to refine the geometry, refine the geometry later and get some other tidings done. But I think for the most part, this is pretty much done. Okay, I just remembered something. I haven't talked about the penetration depth, but then that is not very difficult. You could see I could always go back into the code, and all I need to do is to shift this dimension. So I could as well just give an example now. So defining a penetration depth, I'll call it PD, obviously. Okay, I already have a PD. So what I just need to do is to shift this coupler downwards by the penetration depth. So I could just, yeah, just real quick. If it's not real quick, then I would have to. So I'm shifting this. So what I'm just doing is shifting the 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 Y minimum. So I'm actually going to make the Y minimum Ri minus PD. And that's it. I have my penetration, which I define as the minimum, the the depth inside of the beam pipe. So I could have this, then I could now move, because I want to move just this bottom part into the coupler. I could actually change the whole of the R by subtracting PD, such that when I move it into a coupler, the shape of the coupler doesn't change, but then just the penetration changes. And I think I'll do that. Do bear with me. And that is just as easy as adding minus PD here plus this, and then it shifts it, and go to this minus PD. So it shifts that, and then, oh, of course, this is going to be minus PD, and then this is going to be minus PD. So it's just minus PD to all your Y dimensions, basically. So this is going to be, okay, I think I'll start with this. Yes. This is painful. So I think, yeah, I think you get the point. It's just going to be adding minus PD to all of your geometry, so that PD actually controls it, so that once PD is equal to 0, then you have the shape we modeled initially. So I think just to save time, I'm not going to move it in. Maybe I'll model it and shift it in, and then, okay, I'll just do it now, and but then pause. Okay, back, and voila, all done. And just added or subtracted the penetration depth from the Y dimensions, and then from this, now I could move it. So if I should change this to, let's say, 40, and update, then, yep, you see, so it moves the entire geometry a bit further inside the beam pipe. So that's it for this video. It was a very long one. Hopefully you learned a thing or two from this, not just on couplers, but then, okay, not very much on couplers, but at least on modeling and some ways to tackle some um, seemingly complex geometries. So that's that for this video. One last thing, because I like to do it, and that is blending. So blending this to D1 divided by 2. Preview. And yes, now I can call it a day. So this maybe remove the working plane, and this is what we have at the end of the day. Yep, and this is what we wanted. So that's it for this video, and maybe see you next time. Bye.